lecture, and then it will be posted on YouTube. Okay, anyway, who is absent today? In Labano, One, same as usual. And Ngwako Mokitsi. Where's Ngwako? Okay, so let me continue. So as I mentioned, we're going to finish the topics for long test 1, and it will be up to transformation matrix, which will be the last. We'll just discuss a little bit. We're already going towards that, finishing the topic, and then we will continue on with the next topic. The next topic of Denevit-Hardenberg Convention, we're not going to have that in the long test 1. Or we'll see. If there's something that worthwhile, because I thought I cannot finish it this time. If our discussion is good, then we can possibly include some part of it. Okay, but maybe no, because there's no lab exercise on that one. So let's not do it. Okay, only those with the lab exercises, the one that we'll have included in the long test 1, because that's the one that you have already practiced. Okay, so let me share my screen. Okay, this is the Denevit-Hardenberg. Okay. Okay, so we stopped last time in the relationship of the rotation matrix, the rotation matrices, where we say that if you have a vector with respect to the x, y, and z axis of vector p, okay, this is vector p, where you have okay, that's your vector p with respect to x, y, and z axis, as well as u, v, w axis. And so we can express from the vector p with respect to u, v, w reference frame with respect to x, y, and z reference frame by multiplying with the corresponding rotation matrix. And we can also do the same thing. Instead of x, y, and z, with respect to x, y, and z, we can express the same vector with respect to u, v, w. That means the other way around. Okay, so if you express it with respect to u, v, and w from p of x, y, and z, then there's another rotation matrix that can define that relationship. And so we say that if this vector is expressed from from the x, y, and z frame into u, v, w frame with this by a rotation matrix Q, then we also say that you can do that from u, v, w reference frame to x, y, and z reference frame with rotation matrix R. So the question is, what is the relationship between R and Q? So we say that R is the inverse of Q. Okay, and because of the commutative property of the dot product, we can see that by manual computation, you can verify it yourself, that the inverse of the rotation matrix is equal to its transpose. And so therefore, we can say that Q times R, which is the both rotation matrix, where one is the inverse, will become identity. Okay, and I give this one as an exercise in your lab to prove that those are the inverse of the orthogonal, this is orthonormal matrix, orthogonal and unitary matrix is the inverse of an orthogonal and unitary matrix, or an orthonormal matrix is its transpose. Okay, so let's have an example. Can you read this one, Mr. Rapileng? Can you read this? Ah, you cannot. You don't have microphone. Can you read it? No microphone. Okay, Horata, can you read it?
Given 2 points A subscript UVW is 432 transpose and B is equal to 624 transpose. With respect to rotated OUVW coordinate system, determine the corresponding points A, B with respect to the coordinate system if it has been rotated 60 degrees about the OZ axis.
Okay, so we have, let's draw so you'll have a better overview of what's going on. So when you have O, V, and W axis, UVW. The O is the origin. So you have O here, that origin, and U, V, and W. So U, V, and W is similar to X, Y, and Z. Okay. So now you have A and B vectors. So where is A? 4, 3, and 2. So with respect to the X or the U, 4. Let's just say this is 1, 2, 3, 4, somewhere here. And then 3, 1, 2, 3, and then 1, 2. Okay. So let's say you are here somewhere, and we are here somewhere, and two units here. So your vector is something like this. You understand? Yeah, from the origin, it looks like that. It will look like that. Okay. If we draw the box, this is the box. There. Okay. So this is 4, and this is 3, and that's 2. That's your A vector. And now your B vector will be 4. So there's a 6 and a 2, 6 and 2. So 6 here and 2 here, like that, and 4. So it will be higher, 4. It will be like that. Okay, you understand? So a 6 and 2 here, the box will be higher. Like that. Okay, and then I will highlight this. Maybe I'll highlight this as a green. So that is a vector. This is the vector B, and this is the vector A. Okay, so it's better to see with a box. It's a lot clearer on how are the vectors oriented. Okay, so now the question is, we are going to determine the coordinates, the corresponding points x, y, A of x, y, and z, and B of x, y, and z frame. So that means because we are expressing now the vectors in terms of U, V, and W reference frame. That means there's an x, y, and z reference frame that looks like this. So again, that's a 0, and the x, y, and z, and your another reference frame of UVW. Don't know how it is oriented, but let's just say that's how it is oriented. So U, V, and W. So that means this box here, if you draw it, it will be like this, similar. So your B will be here. You have to draw the box. To draw the box here, 6, 2, and 4, like that. Then the box, do you see it? So your box of 6, 2, and 4 will be this one. This is your vector. And the other one is 4, 3, 4, 3, and 2. Like that. Okay. and your vector is here. So I'm just rotating this with respect to that, okay? Do you see what I'm trying to draw? Make it this one. So this is your A vector and this is your B vector, okay? These vectors are same vector as the one that you have in this frame. The only difference is that this frame is rotated. So now we say that the rotation, frame of rotation with respect to from X, Y, and Z into UVW is around Z frame of 60 degrees. So if we draw that, it will be, okay, if this is your X, Y, and Z, you rotate around Z axis, right? So around Z axis of 60 degrees. Let's say, what is 60? 60 is more than 45, so it will be here. X, okay, this is your new X, but the new X is your V, I mean U, okay? That's how it is being rotated. And this one, I should color it another color. Okay, you rotate by 60 degrees. This is now your U. You rotate another 60 degrees. This is your V. But because you rotate about Z, so your W is coincident with the Z axis, okay? Okay, so that's the rotation. So now the question is, with this kind of rotation, what is now your A with respect to the X, Y, and Z? Okay, and also this kind of rotation, what is now your B with respect to X, Y, and Z? So there's only one rotation. Okay, so now what does it look like, one rotation? So we already discussed the rotation matrices with respect to we call them a basic rotation matrix with respect to the Z-axis. So it is 0, 0, 1 on the third column, and then minus cosine of the rotation matrix, sine of the rotation matrix, or is it minus? No, cosine at the in the diagonal of diagonals is minus sine and sine. Okay, so we just substitute the value and then you compute. Then this is now your A matrix. Any question for the A matrix? So all you need to do is multiply the vector with the corresponding, the vector with the corresponding rotation matrix. So in our convention, we can say that the way this is in another book, I just copied the way they put their convention, but in our convention, we can say that A from, okay, maybe UVW into X, Y, and Z frame, okay, is equal to the rotation matrix of X, Y, and Z with respect to X, Y, and Z into UVW, okay, where you have a vector of UVW of, not P, but this is A. Okay. Any questions? So you just multiply and then that's it. Multiplication is easy, but the way to derive the rotation matrix and all this relationship of transformations will make it a little bit difficult to do manual computation. So next time we will write a program to compute that. But for now, we'll do hand computation for you to understand better. Okay, so next, it is the same vector V, the same vector, I mean B, the same vector B and the U, V, and W axis, which is this vector here. Now we are going to multiply with the rotation matrix in order to express it with respect to the X, Y, and Z frame. So the same thing, X, Y, and Z frame, B from U, B, and W frame will be multiplied with the rotation matrix based on X, Y, and Z frame of R, U, V, W. Okay, where you have U, V, W of the B vector. Okay. Okay, if there are no questions and everything is the same. So here, the rotation matrix, you're just pre-multiplying the same rotation matrix, only the difference is the vector. Okay, so now your new vector is this. So how does this one look like? Is it the same? Okay, let's check. So here, okay, let's just check B. Okay, if B is rotated here, so 60 degrees, right? No, because we rotated by 60 degrees. So this should be the one. So if we say your U was, okay, where was the B? Okay, let's draw the 4. So it was 4 here. Let's just look at the B. 4, 6 in the U. So 6 here and 2. So 2. Okay. It is from the UVW, it's 6. So we draw it from UVW because that's what it is. It is 624 in that frame. So we draw it, that one, according to that frame. Okay. So that is the vector. Okay, now this is 6, 2, and 4. Okay, if that is 6, 2, and 4, then what is it in the Y? I mean in the X, Y, and Z axis. So the Z axis will still be the same. The Z axis will be 4. There, no change. Okay, the Z axis will become 4 because this is the same. That's 4. What about the X? So this is 60 degrees. Okay, so X will be cosine of 6 times cosine of 60 plus yeah, this part here will be, and then where is the 2? This part, this 2. Okay, that is the 2 part. So this part, 6 sine of 60 minus this part 2, is this sine of 60 also? This is sine, so this is cosine of 60. So no, this is, if you rotate here 60, this is also 60. So that means this is 30, so cosine of 30. So this is 6 cosine of, is 6 cosine of 60. Then minus, because you are now on the negative side of X. Okay, there, where is that? Minus 3 sine of minus 3. Okay, and then this is cosine of, now this is 30 degrees, cosine of 30 degrees. Any questions? Because here this is 60 and that's 30. So cosine of 60 degrees. What is cosine of 60 degrees? Is this the one? 0.866? I think that's the one. Can somebody check? I think that's the one. Yeah, that's correct. And then, so this is, so it's a negative value. So this is bigger. So it's a negative value. No. We are looking at B, not this one. Should be this one. Okay. Well, the same computation. It is It is not, it is 2, not 3. So that is 2. Can you check if this is correct? 6 times cosine 60 minus 2 times cosine of 30. Can somebody check it? Anyone?
They are the same, sir.
They're the same? No, what I'm saying is this correct? One, when you are doing our own multiplication here. Okay, let's just run Octave. Okay, let's run Octave. So what is that? 6 times cosine of 60. I think this is the one. Okay, minus 2 times cosine of 30. And 30 is degrees to radians. Okay, 4. It's not correct. You said it's correct. This is 16, not 6. 1.26, yeah, it's correct. So that is that one. So next, do you see my computation? Maybe the text is small. We'll make this terminal. This is terminal. Okay, there. Do you see this? Okay, let's remove some of these annotations. Erase this. So we're just looking only at this. Let's remove all these. Okay, so do you see? So this is the same. Okay, let's remove this one also. So this is the same. And now let's continue to compute this one. So if you have 6 now, instead of cosine, because you're going to compute with respect to y, so that's 6 sine of, okay, so this is 6 times sine of, okay, this part, the sine of 60, and then the 2 is now cosine of 60 plus 2 plus 2. This is now cosine of not 60, not 30, but 60, cosine of 60. Okay. So this is sine of 60. Okay, 6.19 there. Okay. So that's how you compute. So again, it is just a projection. You're computing the projections of the vector. So it's easy to see right now. It's easy to see our own computation, because even if we don't look at the rotation matrix, we can just do the projections of the vector along the axis. We can see that and we can compute easily. But this is because it is true, because the vector, I mean the matrix of rotation of the basic rotation around the x about the z axis is a simple matrix. But if we have several rotations already, then it will be very difficult to resolve the vectors along certain axes in order to find the resulting projections. So what we need to do is now we don't rely anymore on geometry, but we rely on the matrix computation. Okay. So next, let's remove all the annotations. Okay. Okay, so if you again is another example. If, for example, if we express in terms of the if we express in terms of the A, U, and V given, that you are given an A, given the A vector in X, Y, and Z, and then we say that we are computing for the A, U, and V. Okay, can just somebody read this one so that we can look at it if it is exactly the same problem? I think it's not the same problem. Sikabo, can you read it?
In my voice, example, if A xy equals to 4 to 2 transpose and B xy equals to 6 to 4 transpose are the coordinates with respect to the reference coordinate system. Determine the corresponding points A, UVW, B, UVW with respect to the rotated or UVW coordinate system if it has been rotated 60 degrees about the OZ axis.
Okay, so now we are given the A, X, Y, and Z, the both vectors A, X, Y, and Z, and B, X, Y, and Z. The values are the same as the values on the previous problem, but they're expressed in different reference frames. Okay, the same values here, but they're expressed in different reference frames. So now we need to express this X, Y, and Z in terms of U, V, and W coordinate system. So what is similar from the previous problem is that the rotated UVW coordinate system is rotated at 60 degrees about the OZ axis. Okay, so if we check, yeah, let's have I prefer here because there's a whiteboard that we can write on. Okay, so the same thing we have I want to have just the white. Okay, let's have so you can see it properly. Make this one smaller. Okay, so now you have exactly the same rotation of U, V, and W axis from X, Y, and Z axis. So we still draw the same frame of reference. So you have X, Y, and Z, and OUV coordinate system with respect to rotated OUV coordinate system. Okay, so the OUV is rotated 60 degrees. That's that one that we have drawn before. So U, V, and W. Okay. Now, okay, maybe that one you cannot see. Okay. So the question now is, how are we going to express the vectors